going to kick it off.
Sounds good. Thank you so much, Jessica. Good day to everyone, and thanks for joining for another Fluence webinar. I did see some familiar names on the sign-up sheet, so again, I appreciate the interest there. For those of you that we haven't met or we don't know yet, just by way of background, so my name is Jason Bowman. I'm the Director of Industrial Wastewater and Biogas for Fluence's North America operations. For those who aren't as familiar with Fluence's industrial division, we have a specific focus within the food and beverage processing markets where we provide solutions ranging from anaerobic digestion, which is the topic of today, to digestate treatment, to more advanced high-strength wastewater solutions. So for the purpose of today, we'll focus everything around our digesters and digesters in general, and let's say a more unique option for using recuperative thickening methods to improve existing digester performance. At the end, we're happy to answer any questions that you may have, so you can use that Q&A section and post any comments or questions. If there's something more detailed or you want to carry the dialogue a little further, that's fine. You're more than welcome to use my email, give me a phone call. More than happy to talk to you one-on-one. So with that, I guess let's get started. So what I propose for today is to first focus on a brief background on digesters and how and or why there are so many different forms and styles of digesters out there. And then we'll discuss the specifics around how recuperative thickening plays a role in supporting and or stabilizing existing digesters, and not only that, but specific types of digesters. And then finally, we'll talk about how we actually implement this recuperative thickening technology and the steps for ensuring successful rehabilitation of existing systems, but also for new systems as well. So let's get the basics out of the way, just a bit of digester 101. I imagine, or I expect most of you probably already know the basics here, but it's always good to cover. So what do we know about digesters? Digesters are largely applied to wastes or wastewaters or feeds and feedstocks with high organic content. And this content can include high solids, or maybe organic loads are more dissolved and might have lower solids. We'll talk about the difference between those two and how that generates different forms of digesters. But based on the type of feed that we're using, we're going to have different forms of digesters. That's why different digesters exist. But all of these digesters have one thing in common, and that is they produce CH4 or biomethane from organic wastes. So a properly designed and properly operated digestion system should be capable of creating value in a few ways. First and foremost, they reduce organic load and solids loads, which if you're focused on hauling or logistics in many cases, this is a benefit. Second, they can enhance byproducts, meaning if there's like a spoiled or broken, damaged, loss, or unwanted byproduct material into a liquid solid form that can then be stabilized and suitable for land application or even nutrient recovered from that waste in a lot of situations. The third obvious benefit is generating biomethane, which can be used for electrical and heating needs, made into alternative fuels, or feed the local natural gas pipeline in a lot of cases in these big regional digesters. So all this to say that digesters can be used for solids reduction, wastewater treatment, and or localized or regionalized energy generation systems. So I think by now most of you know that digesters come in many forms. So beyond that, they also come in many project models, and that's important to discuss as we go into the recuperative thickening discussion. Some project models focus on maximizing biogas output for recurring revenue. Other models focus on digestion as the most, let's say, economic or holistic method for waste reduction on site. And sometimes those two co-align or one and the same. There is a reason for this, which is that not all waste is created equal. Different industries produce waste or wastewaters with different chemical and organic makeups. You've probably heard me talk about this at length in some of the other webinars that we've done. But we find that different forms or different volumetric rates are required based on how the bacteria are going to react to the incoming feed. So again, this is something that we've covered in other webinars, so I'm not really going to go into too much detail on this today. The point that I'm trying to make here is that at the end of the day, we find that the volumetric loading rates from digester to digester configuration may vary on an order of 10 times. That is, you might have a digester with 1 kilogram per cubic meter loading rate and others above 10. So there's just a wide variance, and that's because of the waste source or the feed source going into these digesters. So the purpose of this slide is just to give a good visual representation of various digester configurations and project models. So we have here ranging from small holistic systems aimed at really more of a wastewater or localized treatment system to larger biogas powerhouses that are generating a lot of energy and create recurring revenue for the operator, for the end user. So before we jump into the recuperative thickening discussion, I just want to note that it's really important to understand the two basic categories of digesters. That is, if you take all the digesters in the world and kind of lump them into two categories, you basically end up with low rate systems, which are your classical like CSTR, lagoon, plug flow digesters, and they're geared more toward a combined high organic or high solid waste profile. And then we have more rapid digestion configurations that are geared more towards lower solids, but a high dissolved organic matter. So each category has a host of variable configurations and loading rates based on the type of waste, whether it's in the meat processing, whether it's in the dairy industry, manure, non-manure, whether it's beverage production, etc. So now we can really kind of turn our focus to the recuperative thickening. So this is, the reason most of you are here today. So what is it exactly? The best way to explain recuperative thickening is that it's kind of like a modified activated sludge process that's built specifically for digester and digestate strengths. We are utilizing a very specific dissolved air flotation system as an initial solids liquid separation step for digestates that is typically applied to lower rate digesters as a retrofit, or perhaps creating a new, let's say, medium rate digester. So basically taking an old school CSTR and kind of putting a new look, a new twist, a slightly higher efficiency mechanism on that. So one important note, note that recuperative thickening cannot be applied to all digester configurations, and I'll discuss why that's important in the coming slides. But generally speaking, this dissolved air flotation process is used to thicken digestate and return a very specific portion of the thickened digestate back to our digester. The point is that most classical digester systems or classical digester designs really have very little control and minimal biomass control. So recuperative thickening allows us to automate the biomass inventory, which provides a much higher operational flexibility. It also allows us to better manage alkalinity and volatile fatty acid ratios. One of the common issues with classical digester systems is that VFAs can build up too quickly sometimes. Basically, digestion is a 4-step process in terms of how the bacteria react. Basically, step 3 in that 4-step digestion process occurs more rapidly than step 4, that is, the methanogenic bacteria can really keep up with, and this is what causes an imbalance in a lot of these digester systems. And there's many more issues, and we'll cover those, but the point is, by having control over the biomass inventory, it really frees up the flexibility, and we can better manage the buildup of VFAs and how the digester itself is operating. So when and where is recuperative thickening applied? Really, anytime that we have a feedstock that is rich in carbohydrates, proteins, and lipids, and solid byproducts, recuperative thickening can be applied to increase the performance and the loading rates of classical digester systems. In most cases, recuperative thickening can almost double the organic loading, that is the volumetric load of an existing, let's say, CSTR or classical style digester, and we'll talk about why that is. So quickly going back to the various forms of digesters and how recuperative thickening can or cannot be applied, knowing where they cannot be applied is equally as important as knowing where they can be applied. So recuperative thickening, again, is applied anytime we have a suspended phase biota or suspended phase biomass, or otherwise really like a normal bacterial flock from digester systems. As you get into high rate systems, a lot of the high rate systems are built around developing granular biomass, and in some cases even like ballasted biomass or fixed film systems. But these systems kind of pose a challenge with recuperative thickening because of the size and the structure of the biota that develop in the high rate systems. So typically high rate systems are granular in nature because they're applied to wastewaters that have starch, carbs, sugars, and they develop a very specific form of bacteria that is a granule that require a very specific form of mixing due to their density. So given that we are taking a modified DAF process for sludge recirculation, that DAF is really not the best fit for these higher rate systems. Typically, these higher rate systems have their own form of sludge management, their own form of sludge separation and recirculation that are not DAF related. So for that reason, we typically only focus on more classical systems or plug flow systems for that reason, where these systems are relying on kind of your normal, let's say, suspended phase bacteria that develop based on the incoming waste profile. So talking about why digesters fail and the need for recuperative thickening or the need to consider this type of process, we typically like to think about failure in two categories. That is design failure, so something we did wrong up front, and then operational failure. What are we doing wrong today? Design failure is almost always associated with having just an incorrect feed characterization. Too often are the inlet basis or the feed basis assumed rather than really being measured or analyzed up front. There's a lot of systems where people think they can duplicate existing systems and apply it to a future system or another market vertical. And you can quickly get into trouble because no two projects are ever the same. It's something that you've probably heard me say many times in previous webinars, but this can be common when digesters are viewed more for, let's say, maximizing biogas rather than an actual waste or wastewater treatment system first. So to put that in another way, basically systems or projects that are putting the value of biogas ahead of compliance or ahead of waste management, let's say. So to name a few other failures, there's failure to account for ionic activity, there's failure to predict toxicity, there's failure to calculate a sulfur mass balance, failure to provide sufficient supporting systems like liquid solid separation steps. There's a lot of different design failures that projects have had in the past. So the operational failures are a bit different. This is when we tend to overfeed or underfeed or overstimulate digesters, letting the chemical and the bacterial balance get out of hand. Other common issues are creating accidental precipitation inside of the reactor. So that could be struvite, calcium phosphate, other forms of ionic activity. And then just the inability to control temperature, right? You don't have the right heat exchanger, or you're having to borrow too much biogas to keep the feed heated to the right temperature. So these are all kind of operational issues. So we typically deal with as Fluence, we typically deal with one industrial source at a time. So that is when we focus more on the point source. So we find it's a bit easier to manage system stability when the feed source is more stable versus perhaps like the larger regional digesters or developer-driven projects when feedstocks and waste can change daily. Feed contracts can change, weekly, monthly, annual sometimes. So, as I mentioned, the recuperative thickening process is generally applied to the lower rate systems. If we focus on why that is and why CSTRs and classical systems fail, or plug flow systems in general, it's almost always associated with a lack of control once we feed the digester. So lack of internal control, whether it's mixing, whether it's the biomass inventory, etc. So recuperative thickening can improve this control flexibility or this control mechanism in a few ways. So number one, we can really control the biomass inventory based on the incoming load. Number two, we can manage overload or underload situations by better managing the biomass inventory and how much we recirculate. Number three, the physical recirculation can actually improve mixing in a digester. So if there's an existing system that has one mixer, two mixers, and it's not really doing the best, there's a lot of solid settling, it's possible to configure the recirculation in such a way that we can improve the mixing inside of the digester. So we're taking existing volumes, existing tanks, and trying to utilize as much as we can that's already there, utilize that infrastructure, but optimize that the best that we can. Fourth option, we can better manage the volatile fatty acid buildup by maintaining a more, let's say, stable mixed liquor or a more stable volatile content relative to the incoming loads. So we can better manage that step 3 and step 4 that I mentioned 2 slides ago. Option 5, in these situations where ammonia toxicity becomes an issue, recuperative thickening can actually be used in combination with dilution to help with the toxicity element. So in those situations, basically the ammonia concentration can be diluted by adding some clean water, while the DAF process really focuses on capturing and maximizing bacterial concentration. So while we're diluting water on the one hand, we're still maximizing our bacterial or biota concentration on the other hand, so that we can recirculate the bugs in a more effective manner and really give them a fighting chance to keep up with what's going on inside of the digester. And then number 6 is really comes back to precipitation. So we often proactively combine precipitating magnesium ammonium phosphate, that is struvite, with the recycle streams in these recuperative thickening processes so that we can minimize the precipitation reactions inside of the digester itself. In other words, we can really address struvite removal external to the digester in combination with a better biomass recirculation. So as far as retrofit feasibility, where do we start? So let's talk about how we go about evaluating how or when we can apply this technology. So first and foremost, we always need to define the reason for existing system failure. Is it the loading? Is it the design basis? Is it an operational basis? Is it associated with temperature control or lack thereof? We generally need to see a complete project picture rather than just tacking on, let's say, a DAF system at the end of a CSTR process. It's really not that simple. There are a lot of other considerations. So oftentimes we'll combine recuperative thickening with secondary heat recovery to maximize temperature control in the recycle, as well as proactively removing the ionic activity or even nutrient recovery in some situations to better help with toxicity, as an example, inside of the digester. So the point is, we must really always understand the mass balance of the organics, the nutrients, the ionic activity, and the ancillary systems to make sure we really understand the infrastructure that's on site and how this recuperative thickening process is going to integrate into that. So from there, we can evaluate the existing digester volume and the resulting organic loading rates. Once we have that concept or concept of the variability in these organic loading rates, we can determine what biomass inventory that we need to control, how much is required, what type of recirculation is required, and if any temperature adjustment is required to stabilize or boost that existing digester performance. In a lot of cases, we can simply go with recuperative thickening and increase the performance in the organic loading rate of an existing system. In other situations, we do go from mesophilic to thermophilic operation, and the DAF system is designed to handle those higher temperatures. But the point is, we can maximize the organic loading and the efficiency of the system even further by combining both of those mechanisms together. So when we retrofit with recuperative thickening, the following process methods are generally considered. Number one, the amount of sludge recirculation is typically proportional to the COD load on the inlet. So basically the higher the COD on the inlet, the higher the recycle rate that we'll have from our recuperative thickening process. Number two, some of you are probably already thinking, well, wait a minute, you're using a DAF process and DAFs have air. You're using this to recirculate. Doesn't the air impact the operation? The short answer is no. The level of solids that you typically deal with in digestates and the level of thickening is much higher than, let's say, your normal DAF operation that you might find in a pre or post biological treatment or aerobic treatment system. The other thing to think about is the saturation values are also carefully controlled in these systems, so we're not just injecting air at a crazy high rate. The other thing with these systems to think about is they're not really designed for mass transfer. The alpha values, if you get into like aeration design, basically the type of air that you're putting into this unit is absorbed very, very quickly, and there's really no residual DO in these type of processes. So not only the saturation values that we control, but the solids loading per unit area with this type of DAF is actually 2 to 3 times higher than what you might find in a DAF system that would otherwise be in like a normal biological process, primary treatment, secondary treatment of aerobic systems as an example. And number three, sorry, with the recirculation, we were often looking to control the mixed liquor volatile suspended solids between 2% and 5%. So you're talking about 20,000 to 50,000 milligram per liter of volatile solids inside of the reactor. And this is based on the incoming load and feed type that we have in these digesters. You will find some variability in that percentage, but that's kind of a general range that we find with these projects. And number four, so the thickened portion that is not recycled can typically be sent directly to dewatering. So we usually use a screw press in our systems, but other dewatering systems can be used. That's not a problem. Kind of a fifth thought in all this is, as I briefly mentioned, struvite recovery in the digestate side stream is possible. This is preferred to do it externally so that we're controlling or preventing unwanted precipitation within the digester. So again, we're doing this externally with a recuperative thickening, so it really helps to improve the overall performance inside of the digester, and this is how we can really incorporate the system and incorporate higher loading rates and higher efficiency. So I had made a note about the DAF or the recuperative thickening process working in both mesophilic and thermophilic ranges. Normally, DAFs and other biological processes struggle with higher temperatures, but with the recuperative thickening process, we can modify the operation for higher temperature if we really need or really want to increase the loading to the digester. So in other words, systems that are landlocked that really need to be supercharged, this is probably the best method. If you're looking to maximize every ounce of organic efficiency in the system, this is the best method to do. And before I leave this page, one final note. While recuperative thickening is largely associated with the DAF design and its function, it is more of a holistic process that accounts, we're taking into account the recycle rates, we're taking into account the solids retention time in the digester, we're taking into account the mixing energy, the temperature, the chemistry. So all of these components are evaluated as a whole. It's not just the DAF technology. While the DAF technology is set up to specifically deal with digestates, it's really, you have to think about these things holistically. You can't just throw a DAF on the end of the process and expect it to double your organic loading rate at the end of the day. So most of the systems that we've applied have been focused on the meat and dairy markets, and this is really where we want to improve digestion for high solids or specific byproducts that you find in the meat industry. Fats, oils, and greases in these systems, even acid whey from a lot of the cheese operations and dairy operations, and then proteins, etc. These are all systems where recuperative thickening tends to be a better fit, versus going to like a beverage facility as an example. So just to kind of put things in perspective for everyone, to give you a visual, a typical project configuration would generally look something like this. So you end up with your existing digester, usually a CSTR, classic style plug flow digester. We incorporate our dissolved air flotation unit on the digestate side. Typically, we're looking at adding a heat recovery pump just to kind of maximize, the temperature element there. We don't want to have to borrow, or I guess we want to reduce the borrowing biogas as much as possible, just so we can, put that biomethane to work elsewhere. Typically, we would have a struvite removal or a dephosphorus unit, let's say, external to the digester recycle. In those cases, what we're trying to do is reduce phosphorus. For those of you that know a little bit about struvite, it's kind of this magic combination of magnesium, ammonium, and phosphorus. It's a 1-to-1-to-1 molar ratio. Sometimes these systems may have an abundance of ammonia and an abundance of phosphorus, but they don't have magnesium. In those cases, it's pretty cheap to add magnesium oxide, where we can physically create struvite, remove that struvite. In some areas, that's sent to fertilizer companies for further processing. In some areas, it can be directly land applied as a fertilizer. It really just depends on the region. But again, the point is that we're using this recuperative thickening mechanism as a holistic approach to digester design and digester retrofit. So with that said, that's kind of a lot to cover in a short time frame. Just to kind of give you, 30,000 foot of fluence in general beyond the recuperative thickening. Just a quick note, for those that are not aware, we are a multifaceted, multinational water wastewater solutions company covering the whole water wastewater cycle. Really, we have 6 main areas of focus, ranging from decentralized and containerized treatment systems to full-scale desalination, full-scale water, full-scale wastewater operations, not only on the industrial side, but also on the municipal side. So most of what we discussed today falls into that last area of focus, which is our waste to energy and digestates. So beyond that, I believe I will conclude here and open up the floor to questions. I'll be happy to take any questions. Hopefully we can get those answered. I do believe this webinar will be posted both on our website and on social media.